Hi everyone. Welcome to session 2. We're going to continue on with our show. I really do encourage everyone to get coffee and dessert, second or thirds for lunch. But go ahead and begin to start session 2 just so we stay on time. And it's also going to be an incredible session on smart and adaptive built environments. It is my pleasure to introduce Dean Nancy Pollock-Elwand with the UA College of Architecture, Planning and Landscape Architecture. She's also a professor of landscape architecture. Dean Pollock-Elwand has an extensive background in cultural landscapes with researching centering on the history of landscapes and urban reform. And I have to just quickly, I hadn't met Dean Pollock-Elwand until we started organizing the summit, and we did these mini sessions to make sure the moderator could meet the speakers and the discussant. And at the time, I thought moderators might just, briefly kind of set the stage, but then Nancy shared with me her presentation. It was so great and interesting, and had such a nice context historically for how we got to this point in time and where we might go going forward. That's why all the moderators have 15 minutes in their time allocation. So you can thank Nancy for that. So please welcome Dean Nancy Pollock-Elwand to the stage.
Great. Good afternoon. I don't know, this is...
Oh dear. Is that better? You're
I'm a bit tall.
A bit tall. Oh no!
I can do one. I can do some.
Okay.
Okay then. Yes, I'm tall. So hello, it's my pleasure to be moderating this session today. The session on, I'll get this right, on smart and adaptive built environments. We're going to have Ray Runyon here. He's going to be presenting his research. And our discussant, Jin Yu, who will be coming in virtually. He's got a recorded piece that will follow. And Paul Hill, our presenter. And then Martin Wiener that is going to follow as a discussant. So, as I said, I am the proud dean of the College of Architecture, Planning and Landscape Architecture. And today I'm going to talk about something that is central to my life, the built environment. So we're going to, but before I start, I just want to explain what happens with the built environment at the University of Arizona in particular. First of all, I want to thank the organizers of this summit. It underscores, I think, this really essential interaction between health and the built environment. And it also allows me to talk about the formidable work of the Institute of Place, Wellbeing and Performance that we partner with, and many of our faculty and students are associated with Esther and her work. Also, the central importance of the building, which is going on right now, the new Andrew Weil Center for Integrative Medicine, which is designed by Tucson's own Line and Space. And the whole ethos of that building, the concept, is about embracing the mind, body, and spirit in the places that we work and the places that we visit for these facilities. And finally, there's the research network that we have at the University of Arizona. And some of you may be associated with that. It's called Restruct. And Restruct is embedded in the, not only within the strategic plan for the University of Arizona, but also Health Sciences has embedded this. And it's about bringing researchers from different disciplines together to focus on the built environment. And so we've got an incredible amount of research which is occurring between medicine and architecture, all the way to mathematics and agriculture. It's just an extraordinary grouping of disciplines that are coming together. So, with that, before I go there, sorry, I'm going to talk about this, is that our gathering today is a perfect demonstration of how the built environment touches upon all fields in every aspect of lives, but in particular, health. And I'll just give you a demonstration of the ubiquity of that. So If you want, you can close your eyes. But this morning, when you woke up, did you have the great fortune of being able to open the window? If you did you breathe in the morning air? What was the quality of the air that you breathed in? Was it noisy outside? Did that noise keep you up all night? Did you get a good sleep last night? I did. But did you take a drink of water in the morning? Were you confident that the water quality that you were going to take in was okay? You had no worries about it. But there may be other people who might be able, they'd be sort of second guessing that quality if there had been an inundation of the water treatment plant in their community. Did you catch the public transit here? Did you have to walk from your house to the public transit node without a sidewalk, which happens a lot in Tucson, as a matter of fact? Did you, along the way, have shade? Were you protected by shade on a sunny morning as you came to work? At work, well, imagine this is yesterday. At work, did you have the opportunity to stand and sit down during the day? Did you have that option to do that? When it got to lunch and you wanted to grab something to eat, do you live in a food desert? Could you only go to fast food to get the food that you wanted for lunch? And several hours into the work that you were involved with, were you starting to get tired? Your eyes start to get a little gummy. You're yawning a lot. Might have something to do with the air in the place that you're working. And was the sun shining in on your monitor? And all through the day, you're trying to fight this shine on the monitor, and it was giving you a headache. So all of these things are the built environment, from the very small scale through to the city. So at this summit, we add healthy aging to the equation. And there's so much to investigate here at different scales and different typologies, different professions and disciplines that it brings together. So today we're going to be talking through the lens of environmental science with Ray and the work that he does, and psychology with the work of Dr. Hill. And we'll be, as I said, we'll be calling upon our discussants to further the conversation. So, but first I'm going to talk about something that I'm very comfortable to talk about, and that's because I'm a landscape historian and also a landscape architect. So I beg your forbearance in what I'm going to now give you as a little context, a little bit of history of the health and the built environment. So what you're looking at there, has anyone been here, is Villa d'Este, outside of Rome. It is in the Italian countryside. It is actually the genesis of that began in the classical Roman period and its heyday in the Renaissance. And it was this escape to the countryside called villeggiatura. And it was an annual exodus that happened of the elites that were resident in the city. And this happened during the very hot summer, when they were seeking some reprieve or some, to relax during the summer, to escape the stench, the heat, the disease of the city, the miasma of Rome that they were escaping from. This resulted in these magnificent gardens and estates that we have in the Italian countryside, and many other countries, particularly in Europe, did this. So this is a strong tradition. So think about this. Anyone in the room have a cabin in the woods? Do you take off during the summer or with the winter or summer to some idyllic vacationing spot? Do you, oh my gosh, build your own personal paradise in the backyard? But what about those, however, that don't have the ability to escape to the countryside? And this was a question that concerned many in the 19th century around the public health movement that was occurring in North America and Europe. Was it altruism, or was there a concern for civil uprise that could potentially occur? The conditions of industrializing cities, and this is happening now, of course, in Southeast Asia and in India and China, parts of China and so on, were so crowded and deteriorated, lack of clean water, proper handling of waste, lack of sunshine, recreation for children, and the spread of diseases like tuberculosis and cholera and typhoid and dysentery. There were also many that rose to address this challenge: charitable organizations, social scientists, medical practitioners, and city administrators. And for me, as a landscape architect, the one that I focused on was a creator of Central Park, and that's Frederick Law Olmsted. He catalyzed these sentiments of concern about public health into urban parks, into park systems, into suburban communities, into the advocacy for national parks. So it began with Central Park. In 1858, it was an oasis, as Frederick Law Olmsted said, sanitary advantage of breathing. So that's amazing. Olmsted worked with Calvert Vaux on the iconic Greensward Plan, and you see the basis of that in Central Park today. So this intimate connection of the design and public health were demonstrated by the fact that Olmsted left his work on Central Park during the Civil War to serve as a general secretary of the United States Sanitary Commission. This was a precursor to the Red Cross. And for Olmsted, for him, the parks were all about the health benefits: active recreation for playing fields for children, to gentle perambulations going through the park, if you've ever had that experience on the pathways, access to clean air and sanitary environments. They even had a dairy for children to get fresh milk every day. So here the physical health of the city dweller was thought about, but also mental health. Interesting, because he believed that scenery and exposure to beauty were very important in one's health. So he is quoted to say, the reason why we have these open spaces is to increase the subsequent capacity for happiness and the means of securing that happiness. So the design objective that Olmsted came up with way back then has currency to today, because you hear about the stories of people who went during the pandemic to open spaces because they didn't fear that they were going to catch COVID from one another. So it still continues. So I'm going to finish here quickly with the built environment and the research which is occurring in the built environment. And the first, and if I to categorize the work that's occurring with the built environment, there's 3 areas, and I'll give you 3 examples of that. One is in health, and I'll talk about this particular research. The other one is in well-being, and I'll talk about this one. And the final one is about aging. So first, on the first one on the top right, this represents actually the seminal research of Robert Ulrich, who in 1984 looked at the influence of a view outside of a hospital window in terms of the health of a recovering, or the rate of recovery after surgery, one of those studies. The second one down on the right is a more recent use of MRI imagery, and this is done by Tang and Associates, 2017. And he was looking at the well-being produced by different kinds of views and landscapes, be it urban or mountainous, forested, or water bodies. And then more recently, the one on the bottom left is actually the work of a colleague of mine from the University of Calgary, who prototyped aging in place structures. And these are small houses used with embedded digital prompts for memory loss. Also, you look in the mirror and you can actually connect directly to a health practitioner through the mirror. Lighted strips along the baseboards to allow people at night, when they get up and their eyesight is not so great, that they can find their way to the washroom. Adjustable heights on everything, in the bathroom, in the kitchen, you name it. So what's really most intriguing about this is that the people in Calgary, actually, or in the province of Alberta, are now considering the notion of a small house being prescribed by a doctor. So fascinating stuff. So these advancements in the built environment only occur because of the collaboration of researchers. And the two presenters that we will have here now speak will be talking about that. And these collaborations, for those in the built environment professions, allows us to imagine what can happen and ultimately build what can happen one day. So thank you. So now I give you, and that was right on time. Now I give you Ray Runyon, who's an assistant research professor with the Department of Environmental Sciences at the College of Agriculture and Life Sciences at the University of Arizona, with his work on ambient light and thermal comfort. Ray. So should Ray, how would you like Ray to?
Just use the mic at the.
This is just my filler, by the way. These are my grandkids. And a moment of awe for you.
So Ray, it's up to you. Would you like to try this, or do you want to?
I can hold
Just
the
hold it.
microphone. Yeah.
There you go.
So it's on.
I'll let you. We'll just put this over here.
And we're just using like normal, just using the arrow.
Okay. You could do the arrow, or you
Okay.
could do.
Okay.
I think I might be messing you up here. Second. Okay.
Okay.
Yeah.
Hi. I'm Ray. Thank you, Nancy, for the great introductory talk and for the introduction. So yeah, I am. My department is environmental sciences, and my background, forewarning, is chemistry. So we're going to take a little bit of a spin on someone who develops assays to try to measure our response as a human being. And I do a lot of my work with the Andrew Wild Center for Integrative Medicine. I'm trying to figure out where this. Okay, there's the screen. And so yeah, so I work most of my work with the Andrew Wild Center for Integrative Medicine, and my interest here lies in sweat, human sweat. What can we measure in human sweat, and what can it tell us about how the environment is impacting us? And what kind of data can we collect, and how do we develop that data? And so this is a team that I've been working with, listed here. And this team, we've been focusing on the impact of ambient light in the built environment. So warm light and cool light in the built environment, and how can we measure if that has any impact on how we perceive the temperature, or what our thermal comfort is in that environment. And I think, looking forward, the goal here could be that if we can use light to help us have an impact and help us be more comfortable temperature-wise in a room, then we may be able to reduce energy consumption with buildings. And if you think about how many buildings there are, that could be a huge impact on many different areas of energy consumption, environment, and things like that. So, but this is a team, and they're all wonderful people to work with. So this is a image that we refer to as our layer cake image. But the concept here is that on the bottom there's the person, and then layered on top of the person are a multitude of different environmental attributes, built environment, natural environment attributes, and they are constantly impacting us, and we are constantly adjusting to the impact of those different variables in those different environments. And they impact our social behavior, they impact our physical health, they impact our well-being, they impact our stress, our resiliency. And if you get down to the very sort of bottom and you start to think about the person, you can think, not only does it impact us, but we also give off signal. We also give off data that can be collected to help us understand what might be going on with different variables in the environment. And that's what I'm trying to do from the analytical chemistry side of this project is understand how we can collect some of that data, how we can do it non-invasively so we don't have to poke and prod people, how can we integrate that into the built environment, and what might it tell us about how the person is reacting to that environment. So one of the ways that we do this in my work is using thermal imaging. So we have some high resolution IR cameras, and we can focus those at different areas on the body. And that's what we're showing here. So on the left is just a thermal image without processing. And we've worked to develop various filters, and we can do layers of filtering and eventually wind up with an image on the right where that is basically distilled down to what we're identifying in the image on the left. The image on the right is distilled down to, I don't know how to make it go again. That's okay. You saw it flashing. What we believe are actual sweat pores on the surface of the skin. And you notice that they were flashing. Some were staying, some were flashing. So that's sped up about 8 times. But that's just showing us that in just sitting down, focusing a camera on the outside of the ankle, we have sweat pores that are turning on and off in real time, all the time. So our question is, can we measure that? Can we collect that? What do we do with that data? And can that be impacted by the built environment? So we call this our sweat pore activation technology. So we're actually monitoring the on and off of sweat pores in real time. Okay, that one, we'll skip over that one for a second. So the slide here is showing our sweat pore activation data. So this is just us trying to compare this data. Are we on to something? Do we have something that is comparable to known gold standard? In that case, we compared it against skin conductance. So you can see on the top left, we have the palm of a hand, and they have 2 electrodes there, and that's our skin conductance response. And that is kind of the gold standard for measuring autonomic nervous response in experiments. You can see the image of the palm just to the left of the sensors. And so we trained, we highlighted that area and we counted the sweat pores we got from that area. So the skin conductance is in blue, the sweat pores are in orange. And what we see is that our sweat pore data correlates exceptionally well with skin conductance data here. So this says that we can measure this happening in real time, and we can do it from a distance without actually having to have contact with the human being. And so this allows us now to try to integrate some of this technology into a built environment. And so the environment, in a built environment, there's different attributes that are important for people to be considered, for people to be comfortable, for people to feel comfortable. There's thermal environment, the air quality, which we've talked a little bit about, the acoustical environment, and the visual environment. And the purpose of our experiment here, or our project, is to try to use the visual environment, lighting, to help us have thermal comfort and reduce energy consumption in buildings. And here is an example, or a couple of images that show an example of the type of lighting that we can put in an environment and have control of. On the top is warm light, or warm white light, around 3000 K, and on the bottom is more daylight light, so what we would call cool light. And we see, again, we've just kind of highlighted in bold and underline, the hypothesis that by using lighting to control thermal comfort, we can have an impact on energy consumption. So we tried to mimic this idea of an office setting. You can see with the different lighting, the colors look a little bit different. You can see the difference there. So we tried to mimic that here at the U of A, and using the sensor lab, the Bio5 sensor lab at the University of Arizona. And we have lighting conditions that you can see here. We have floor lamps, and we have lighting in the ceiling in the room. And we can make that cool light, or we can make that warm light. We put a TV in there. We took the desk out and we put a chair, a nice recliner chair in there, a side table. We tried to make it feel more like a living room environment at home or something like that. We installed a heater, and the heater has, you can see the little white plug, that's like an energy consumption monitor on the heater. And then what we want to do is invite people to come into the lab. And so we designed an experiment where we would invite people 65 and older to go into the space that we set up, and we would have them stay for 4 hours, 2 hours under warm light, followed by a break, and then 2 hours under cool light. Or we may flip-flop it around and inverse it. We were supposed to randomize it. The idea is that warm color, people would feel warmer, cool color, people would feel cooler. And we were able to get 3 test volunteers that helped us optimize our parameters for the experiment. And we made it to one, what I'm calling a real-world volunteer, one participant that responded to our request for participants and came into the lab to do the experiment with us. So this is the type of data that we collect. We talked about the sweat pore activation, so we can get sweat pore data. We can get skin conductance response, which we talked a little bit about. We had a thermal camera hooked up to a phone where we could have people take a photo that would give us skin temperature measurements. We had our power consumption, and we sent out survey data. So we did survey data at the beginning and then every 30 minutes through each session. At least that's what we want to do. And questions like, how does the temperature feel to you? How comfortable are you on a scale of like 1 to 100? And so this is the data. This is the real data we collected on one person. So I'm going to sit here and say, yay, we collected data. Like, this is good. We've sort of released our technology and assay out into the semi-wild at this point in time. We were able to collect some data. But so peaks 1, 2, and 3, and 4, what we mean by that is that's each time point that we collected survey data. We also had them measure their skin conductance and collect sweat pore data at the same time. So we can collect data. We can see that there's differences between each time point of data collected. This is in the warm light session. And if we look at the sweat pore data, we can see that it looks a little different between the cool light and the warm light. And I will leave it at yay, we've collected data. We're still working to interpret the data, understand what the data means, improve the data collection and the data processing. But this shows that we can implement and integrate this technology into a built environment and collect data from a person. And I would believe that if we collected data from a broader population and more people, that we would begin to see more inferences in the data and then begin to potentially differentiate between warm and cool light. It's a little bit difficult with one kind of data point, but we're there. We're collecting data, and so this is some of the conclusions here. That feasibility, yes, we can implement the technology into the built environment, at least to collect this physiological data in a sort of new way of doing it with a thermal camera. But we need more participants. We did notice that the room, we targeted 65 Fahrenheit. It really stayed about 70. So we think we might need a little bit better control of the room temperature. And really, we need to have a bit more seamless integration with the technology into the room. We've talked a little bit about how there's just a lot of technology to consider. And so I think we need to make it a bit more seamless and integrated. So, but that's where we are with this project and trying to collect physiological data in built environments and understand how the lighting and the temperature impact that.
Our respondent, Jin Yu, is joining us.
You want to use the mic?
Oh,
How do we get up?
Let me help you.
so our respondent is Jin Yu.
Would you like to sit?
Right here. and he's joining us with a recorded response. Dr. Jin Yu is a director of machine learning at Signify, and he's based in Pennsylvania, and will be joining us virtually.
This is Jim from Signify, and I appreciate the invitation to be discussant for this topic, and I'm very sorry I could not join you on site. I'm Director of Machine Learning at Signify Research, and we were Philips Lighting, and we are still the world's largest lighting company. We have about 120 million connected lights as of now, and many of them have embedded sensors, from motion sensors, occupancy sensors, thermopile sensors, humidity sensors, temperature sensors, many different kinds of sensors in our light. I'm leading the team here using the IoT system data and sensor data to build the applications, including space management, energy optimization, elderly care, etc. I really like the topic Ray presented, since both lighting and energy are very close to what I'm doing here every day. Circadian lighting can improve sleep, productivity, and the energy saving could save our Earth. 1 Celsius degree change means about 6% energy saving for commercial buildings. I haven't seen the related research using color temperature to balance the thermal comfort and the energy saving. And the initial results with 3 subjects show some promising results. Therefore, I look forward to the final number of energy saving with this technology. I have the following 3 comments. The first one is since the simulation of daylight from morning to evening gives the best circadian lighting, continuously using warm light might have some impact on the circadian health, which could result in low sleep quality, less activity, etc. Therefore, I will suggest a combined research between circadian health and energy saving. People's thermal comfort or sensitivity have a big individual difference. Men and women, young and old people have such a difference. My second comment is how can we integrate this into the HVAC system to address this problem? Can we build a feedback loop between thermal comfort and the HVAC system? The third comment is other environmental parameters such as airflow and humidity could also affect the thermal comfort. Should we consider these parameters since there might be difference from buildings to buildings across the different regions? Generally, I think this is a very interesting research if we can prove this with the test results. Hope everyone have a great day and look forward to meeting with you next time. Thank you. Bye.
So Ray, would you like to respond to anything that Dr. Yu had to say first before we go into questions and answers?
Yeah. So thank you for the comments and the responses. I want to respond to the question of building into the feedback loop for the HVAC system. That we did discuss that during the preparation of this project, and that was really a curiosity question we had. And I think one of the things that we proposed in here is that once we understand this data towards sort of personal thermal comfort, that there is the potential that it could be built in ways to help individualize the environment for the individual. With respect to the airflow, again, that is a variable that can be difficult to control, and it's different with every building and every environment that you go into. And so we chose the U of A Sensor Lab to conduct our experiments because we can control so many of the environmental variables, which hopefully that allows us to amplify the impact of lighting on any sort of measured perceived thermal comfort versus variations in airflow or HVAC systems. So, but I agree. Every environment is unique as a person, and so having some feedback loop would be, a great end goal for some of this work.
Thank you, Ray. Yes, question.
I just had a question about time of day and timing of the assessments. Given that point about circadian rhythms, is it better to start in the morning with these sorts of 4-hour assessments, or does it matter?
So, I think it would matter and be ideal to have our subjects come in at the same time points during the day. Again, the counter argument with this is we are dealing with human beings who have free time when they have free time. So we do our best to try to set it up, but we do want to try to have. It would be ideal, like I said, to have people come in during the same points of the day. And I think I mentioned that to sort of deconvolute the impact of the lighting environment, I think it is important for us to randomize when people get warm versus cool color. So why we have to consider the circadian rhythm also, that could have the difference between getting warm light or cool light first might also impact our measurements. So.
Yes. So we've got a cue.
Sorry. Hi.
Thank
Lee.
you, Tara.
I'm here. Hi.
Esther.
Esther Sternberg. So full disclaimer, I'm research director at the Andrew Weil Center for Integrative Medicine. I kept a long arm to not have any conflict of interest with Ray Runyon and his team, and I think it was a great job. Very complicated, many moving parts. But to answer the circadian and sleep question, when you started, the only space available to do this kind of study at the University of Arizona was the sensor lab. And now, last week, Dr. Sairam Parthasarathi opened up a $5 million new sleep center, the Center for Sleep and Circadian Science, funded by NIH. Thank you. I don't know if it was you. But which has the ability to control airflow, carbon dioxide, lighting, and to measure every aspect of circadian rhythm, sleep, and EEG, you name it. So I'm sure that he would be happy to have you added. Take all your equipment from the sensor lab and put it in the sleep lab.
Thank you, Esther. Yes.
Thanks, Ray. I had not seen your sweat pore data before. I've seen others of your measurements. And I was wondering what you're thinking about, maybe this is getting into the weeds, but of what that is actually measuring. And for example, I noticed that the sweat pores seem to spike at the very beginning of the movement, whereas the skin conductance is extended across the time window of movement. So is there something specific that you're thinking you'll get from sweat pores that you wouldn't get from skin conductance or from actually the contents of sweat, that kind of thing?
Yeah, so that is interesting, right? They both seem to kind of turn on at the same time, right? So that's the sweat pore being activated and the sweat pulsing out. And then you get that latent return to baseline with the skin conductance. And I think I think what we're getting with the thermal imaging is a bit higher resolution of the on-off, the pulsing of the sweat pore. And I think what the skin conductance is giving us is that's always a closed circuit as long as there's something there. So there is an impact of evaporation and time and what's left on the surface of the skin. So I think we're getting at a little bit more with the imaging, a little bit more visualization and measurement of the fundamental process of the sweat pore going on and off in real time. And then the question is, are we measuring the same sort of activity as, sympathetic, parasympathetic responses in the same way? So there's still more work to be done there.
I just wanted to make a comment, and thanks for your presentation. It was great. During aging, circadian rhythms change, compared to we tend to shift back or earlier a bit. And so in comparing your adults and older people, you may have to do this is a huge experiment. You're going to need a really big grant to do this.
Thank you.
You should get one. But you probably should take it, consider different times of day, and in your comparisons, it will be different for an adult's peak activity and an older individual's peak activity, probably.
Do we have
Thank
any people online? Did you respond to that, Ray?
Yes, I agree, and I think right now, what we've been able to show is just that we can take the measurements and they can be, validated against some gold standard approaches, and we definitely need more than one participant to come into the lab.
Thank you. Mindy.
Yeah, great talk. And I think you'll need even more money to do this study. Well, because in our languaging, we're saying older adult over 65, but I think just to emphasize that there are really multiple cohorts of older adult, 65 to 74, 75 to 80, that there are really, except to sort of almost three groups of what constitutes older adults. And I imagine, there's a very big difference between a 65-year-old and an 85-year-old. So you're going to need even more money.
Thank you again. I'm just throwing it out into the universe in case somebody wants to give that back.
Kathy.
I think you should measure age continuously, but that's a side point. Teasing you. Ray, thank you. The thing that I'm concerned about, I didn't hear anything about the quality of the sweat and whether or not you were looking at that, and if that isn't also important to look at the inter-individual differences, between people. So could you comment on that? Did you look at what's in the sweat?
So in this project, we are looking only at sweat pore, implementing the technology for sweat pore activation. But across the broader program, we do look at biomolecular signals that come that can be found in sweat, and that is as unique to individuals. I mean, it's unique individual to individual. I think some of the extension of this is you saw the flashing patterns of sweat pores in the video, and that leads us to ask questions like, are those patterns different if we have emotional sweating versus physical sweating versus cognitive stress sweating, and if that could lead us to hunting for different types of molecular biomarkers based on the patterns that we can get there. So we work also in unique ways to collect sweat from people and things like that too. So, but in this project, we were trying to implement the thermal imaging technology into the environment.
So what I'm thinking too is the number of chronic illnesses among older adults, and how those influence sweat. So just other considerations. I think it's very complex, but thank you. Thank you. Really interesting talk.
Thank you.
Thank you. Are there other questions? We've got 5 more minutes. Do we have anything online? Nothing online. Okay. Oh, yes.
This is very interesting thinking, and I appreciate your presentation. One of the characteristics of comfort is ventilation, and you can have a higher temperature room if you have a fan on and be more comfortable. And so I'm not sure if your participants were short sleeves or long sleeves. Those kinds of factors might have an effect, but just making sure that the ventilation is consistent for each of the participants as well, because that'll have a big effect on comfort.
Yes, we try to keep the room conditions constant as much as allowed. And we actually have them where all the participants will wear a white t-shirt, so we don't have any differences that may occur from fabric or color of the fabric or long sleeve versus short sleeve. So at least we try to normalize that as much as possible. So we do the best we can.
Wonderful. Other questions? Well, all I can say, this is perfect research coming out of Tucson when you talk about sweating. So I'm feeling a little sweaty myself here right now. But anyway, thank you, Ray. That was wonderful. Great discussion as well. Thank you. I guess I've got lots of microphones. Great, thank you. So may I now ask Dr. Paul Hill to come to the front. Dr. Hill is a research scientist with the Department of Psychology at the College of Science at the University of Arizona. His presentation today takes us to the supermarket and his study of healthy aging and disease. Thank you. Oh, you need that.
All right. Yeah, well, first of all, thanks for the invitation to be here today. I've been a part of the University of Arizona for about 2 years now and really impressed by the breadth of aging research that's being done here. So it's really exciting to get to be here and hear about all this different research. So in our lab, we study memory, spatial cognition in humans. And so I'm going to talk about some of our research today, examining spatial navigation in healthy older adults. So when we talk about spatial navigation, this refers to a collection of behavioral processes. So things like being able to orient in space, learning and then remembering locations within an environment, getting from point A to point B and so forth. And unfortunately, as we get older, even during otherwise healthy aging, our spatial navigation abilities decline. That's just one of the things that goes as we get older. And these deficits, these spatial impairments seem to be exacerbated by early stages of Alzheimer's disease. So because of this, there's a lot of interest in trying to better understand the source of some of these spatial challenges that we experience as we get older, both associated with healthy and pathological aging. Now, much of what we know about the behavioral and neurobiological effects of aging on spatial navigation come from rodent studies. And there's a variety of different experimental techniques we can use to study these in rodents. A really common test that we have illustrated here is called the Morse water maze test. So some of you may have heard of this. Basically, we put a rodent in a pool of water and we can look to see over time and under a variety of different experimental conditions how well they're able to learn the location of a hidden platform so they can actually climb out of the water. And what we see is that over time, they're going to start to take a more direct route to that platform. So this indicates spatial memory. And it's very well established that aged rodents do worse at these types of tasks, right, compared to younger ones. It takes them longer to learn the locations within the environment, and then their memories are less accurate and precise than younger rodents. Now, in humans, one of the kind of primary measures or approaches we use is to test spatial navigation using virtual reality administered on a desktop or laptop computer. So here you have your human subjects using a joystick to navigate and move around in space. Now this has formed the basis of literally hundreds of prior studies examining spatial navigation, including those examining cross-sectional and longitudinal effects of aging on navigation. However, there's some serious limitations, which some of you may be able to note here, is that navigating a two-dimensional virtual environment on a computer monitor is just inherently different than navigating in the real world, all right? So when we're navigating on a computer screen, we're restricted to that visual input only. When we're navigating in real space, we have much more enriched sensory feedback. So kind of these walking cues, proprioceptive, vestibular, all this information that might be contributing to our ability to kind of learn these spatial layouts that we're not getting when we're testing our human participants on a computer. Not to mention, anytime we're doing cross-sectional research, when we're comparing young and older individuals, we might be observing age differences that are not really related to navigation, but to other, confounds. So things like prior experience with computers, differences in fine motor control and so forth. So there's some limitations with how we have traditionally measured spatial navigation within humans. Now, recently, just within the past few years, and this actually kind of picks up on some of the work that Dr. Palmer was talking about, is the emergence of immersive virtual reality. All right, and so when I talk about immersive virtual reality, I'm talking specifically about the VR goggles, the headsets that individuals can wear that really provides kind of this level of immersion within the environment. So if you haven't ever worn one of these headsets before, I highly recommend it. You can be fully aware that you're in your living room, but it really kind of transports you into a new environment. And so we can actually use this in the lab to test spatial navigation under a much more naturalistic setting. So we can actually now have our participants physically ambulate within the environment. They can actually physically move around and experience this virtual setting, again, in a much more naturalistic way. It also gives researchers, using immersive virtual reality, gives researchers the opportunity to kind of exert some control over the types of environments, the types of information that our research participants are experiencing during a study. So we can actually manipulate certain features of the environment to test specific predictions and hypotheses that would really be challenging, if not impossible, to do in a more real-world setting. So there's a lot of advantages of using immersive virtual reality. And really, if you get anything from this today, my hope is that I convince some of you that using immersive virtual reality technology is a very useful and powerful tool for studying some of these questions regarding spatial navigation in aging populations. Now, our lab recently ran a study where we had healthy young and older individuals. And I see this is an older figure, and I didn't crop it properly. We had healthy young and older individuals come into the lab and navigate a virtual version of the Morris water maze task, so similar to what I showed you for rodents previously, but adapted to make it accessible for humans. And we had them do this in using a traditional desktop-based virtual reality platform. And so what you see is that across 3 different phases of this experiment, we see worse performance in older individuals. So these measures here, just keep in mind, higher bars indicate worse memory performance. This is a measure of spatial precision. So we see these age differences in spatial memory across these different phases of the experiment, which is nothing new. This has been replicated numerous times in prior studies now. However, when we have the same individuals come in and navigate a very similar version of this task, but now in immersive virtual reality, so they're able to physically walk around. Oops. Uh-oh. Okay, one of the animations is... well, I apologize for that. What I was going to show is that these age differences are significantly attenuated. There's still a bit of an age difference, but the magnitude of these age differences are greatly reduced when you're able to physically walk around in this immersive virtual environment. And so what this kind of has this has led our lab to think a little bit more about, how can we develop and create more naturalistic paradigms, more ecologically valid tasks to measure some of these spatial deficits. And specifically, we're interested in developing virtual reality environments that kind of more closely approximate and mirror the types of challenges that older individuals might face in their day-to-day lives. For example, navigating or kind of getting around, getting oriented in a new supermarket. So this is something that everybody's kind of had to experience at some point and can become a little bit more challenging as we get older and certainly during the earlier stages of dementia. So the study that I'm gonna kind of talk about today was inspired by an earlier paper by Kathleen Karasik. So this is a paper from 1991, where they actually had healthy young and older individuals come in and navigate in both their familiar supermarket, so the grocery store they typically go to, as well as a novel supermarket. And I think everybody can probably appreciate the fact that, for whatever reason, maybe you're coming home a different direction, or your typical grocery store is out of something, so you go to that new market, maybe it's a different chain. Everything's kind of laid out differently, but it's a little bit harder to get oriented. So it takes you a little more difficult to find, the pasta sauce or whatever it might be. And so what they actually found in this study was that young and older adults don't really differ across a number of different measures. So, kind of path efficiency, memory, just, overall orientation within that familiar supermarket. It was really in the novel, the unfamiliar supermarket, where we see these vast age differences, where older adults really performed worse. And this is actually now, this kind of general idea has been replicated numerous times. We actually see that, at least during healthy aging, it's that ability to kind of orient and navigate in a new, novel environment where we really see these large impairments. And in fact, it's actually spatial disorientation in familiar environments, which might be a very sensitive metric of early stages of dementia and Alzheimer's disease. So, now this is admittedly an older study. It involved researchers following around their participants with a clipboard and monitoring their behavior every few seconds. So the results are observational and, frankly, a little bit crude and imprecise by today's standards. And so what we wanted to do with this project was kind of bring this idea into the 21st century. So the idea here was to create what we're calling the virtual Quickie Mart. And we don't really see this as a one-off study. We kind of think about this as more of a virtual platform that we can use. It'll be flexible and something that we can modify in order to test, any number of kind of novel predictions and hypotheses about the effects of aging, early stage pathology, Alzheimer's pathology on navigation performance. Now, another advantage of virtual reality is that it also gives us the opportunity to collect a very diverse range of behavioral, biometric, and psychophysiological data. So one area that we're really excited about right now is we have purchased some digital wearable sensors that individuals can wear as they navigate in these virtual environments. And this allows us to collect biomechanic, and functional mobility data and measures as people navigate. So this allows us to look at things like balance, postural control, gait, stuff like that, and to determine whether or not any of these measurements, whether any of these physiological measures might explain a unique source of age-related variance in spatial navigation performance. We're also, our headset is equipped with eye tracking. So this allows us to actually kind of look and examine what types of information our participants are attending to. Do the different age groups differ in the types of information, the different ways that they sample from the environment? And then how well does this predict what it is we remember, what it is we forget within our scene? So we recently ran a pretty small, just kind of proof of concept and feasibility pilot study. So we had 7 young and 8 older adults come into the lab, and we gave them this task. So they were given a shopping list. All right, so they had a shopping list with 20 items, and they had to go through and find all of these items. All right, after they had located each item, we then emptied the shelves, and then we had them take each item and place it back as best they could in the location that they originally retrieved it from. So the idea here is we could test spatial memory. How well are they able to learn the locations of these various grocery items? And we did this in 2 different markets. We had 2 different unique environments. In the first Quickie Mart, the first environment, they went through and they repeated this process until they reached a criterion level of learning. All right, so the idea here is that we wanted all of our participants to become sufficiently familiar with this first market. We wanted to have repeated exposure so they were very familiar with this first environment. We then placed them into a new market. All right, so the shelves were oriented differently, the walls, the windows, everything was different. So it's very clear that this was a unique space. We then had them repeat this process. They had to shop for all the items and then replace those. All right, they did this one time, so this was a one-shot deal. So this was kind of our less familiar, our more novel supermarket. And then after a delay, we had our participants then go back and place each of these items. We tested their memory once again in each of those environments. And so what we see is that during the learning, so within this first supermarket, within this first Quickie Mart, on average, it took younger adults about 2 trials and older adults about 3 trials to reach criterion, that criterion level of familiarity, which is actually maybe a little bit too good. This is the second version. We had to make the task a little bit more difficult. So that's something we're kind of thinking about as we move forward, that we don't want to hit ceiling effects. But I think it's just promising that it shows that both age groups are able to really learn this novel virtual environment. Now, it did take older adults a little bit longer. That's to be expected. Both age groups performed surprisingly well. When turning to the memory data, so looking at delayed recall, we actually see that within the familiar supermarket, both age groups perform really well. So they're able to remember about 15 out of the 20 items. And we don't really see any age differences here, all right, within this kind of highly learned, familiar environment. It's only in that novel supermarket where we see those age differences. So I want to call your attention back to that figure I showed earlier from the Kathleen Karasik paper. And we think that these results kind of provide a nice sanity check and proof of principle that we can actually test some of these types of questions within this virtual space. All right, so we're kind of, even though this is performed in a very different context, we're optimistic that we're able to replicate some of those effects that we're seeing in the real world. All right, so we also, I want to show a little bit of our biometric data. So some of the data we've collected using some of the wearable sensors. And so I'm going to show some data from a postural sway task. So postural sway is a test of balance and postural stability. And these are things that are known to decline as we get older and to be particularly susceptible to age-related neurodegenerative diseases such as Alzheimer's and Parkinson's disease. And so in this test, what we do is we have our participants stand upright, hands on hips, unassisted, and we can kind of look to see, can they maintain that upright position as we incrementally take away different sensory inputs. All right, so this idea of balance, fortunately for most of us, we don't have to think about it. It's pretty automatic. It seems pretty simple. From a neurocomputational standpoint, it's actually a really complex process. There's a lot of sensory information that's kind of being integrated to allow you to maintain this upright position. We think this is really important for navigation, both balance and multisensory integration. So what we wanted to do here specifically is to look and see whether or not having individuals, and especially our older adults, in an immersive virtual reality setting versus in real space, how does that alter some of these factors? How does that alter things like balance and multisensory integration? And this actually kind of picks up on some of the questions that were raised during one of the earlier talks. Now, again, I want to just caution this is all very preliminary, but kind of an exciting direction we're looking to go. And so what we see is that at least during two of our conditions, during what we label here as ocular and proprioceptive, so this is kind of looking at the integration between motor and visual information, and then between visual information and proprioceptive feedback, we don't really see an advantage in either environment. So whether you're in real space or immersive virtual reality, that doesn't seem to be too much of a difference. However, in this vestibular condition, now this is arguably the most difficult of the tasks we had them do. Basically, you have your hands on hips, your feet together, and you have you tilt your neck all the way back, so it's kind of disrupting that vestibular inner ear system. Here we actually maybe see some trend towards worse performance in immersive virtual reality. Worse performance in real space. So we had them do this in just a physical room, an actual room, and in an immersive virtual reality room. We actually see better balance potentially in immersive virtual reality. Not exactly what we predicted. It's actually the opposite of what we would have predicted. So not sure how that's going to pan out. Of course, these are small numbers, so we'll see what the data looks like later. But yeah, this allows us to kind of maybe get at some of these questions about whether or not different age groups and kind of loss of sensory acuity in these different sensory domains might be a barrier to using immersive virtual reality as a tool for both research and intervention. All right, so I hope that I've convinced some folks that immersive virtual reality is a really useful tool. We're really excited about what we can do with this task. We're certainly still working on some additional features. So we have some equipment we're going to actually create haptic feedback gloves. So, currently people are using a controller to interact with the environment, which is still a bit of a limitation, especially for our older individuals. So we have the equipment that we can actually create gloves that allow people to physically they get that tactile and that somatosensory feedback as they interact with objects in the environment. Kind of interested in, using some of this biometric data that we're collecting to see, can we identify any digital biomarkers or any digital features that might correlate with spatial disorientation in our older adults, and maybe using this as a potential diagnostic tool for those that are at an elevated risk for some of this Alzheimer's related pathology. We recently submitted a grant where we will we hope to use the virtual Quickie Mart as a kind of a tool, an interventional tool for training spatial orientation in healthy older adults and those with mild cognitive impairment. So can we actually train people to interact in their environment a little more fluently, a little more comfortably? And then I think taking it back, kind of the general theme of the session is, can we use these types of tools to kind of learn about what spatial features, how can we design environments? What are the spatial features, the spatial cues that can really help these aging and more vulnerable populations kind of interact with their environments more more fluently. So with that, I will just acknowledge everyone who's played a major part in this research, and thank you.
If I can now call Martin Wienert to the front, who will respond.
No, it's just some notes. Sure. Hi, everyone. So just want to say thanks for inviting me out here from across the river just to kind of talk about this. Very nice to be here. It's very interesting stuff. And where's Paul? Oh, there you are. great work also, Paul. So just to give you a little bit of information about myself, so I'm an assistant professor of psychology and bioengineering at George Mason University. I've been there now for about 6 years, and we'll be going up for tenure this fall. Before that, I was actually a AAAS Science and Technology Policy Fellow, where I worked at the National Science Foundation for 2 years in the Computing, Information Science, and Engineering Directorate. And while we were there, VR and aging were two things that were of particular interest to folks developing applications. So certainly this is work that I find interesting connection. My own work does involve spatial navigation and spatial processing. In particular, however, I'm interested also in the perception of time. So how people perceive time and space together, which are two important things. As an interesting connection to things that have been discussed here, both time and space are influenced by awe. So how much awe you experience is influenced by your perception of distance, think vastness and vistas, the Grand Canyon, Monument Valley. But that in turn can also dilate your perception of time, thus making you feel like the amount of time that you're in these spaces is lasting for longer. So spatial navigation gets worse with time. This is the wider context I'm just going to provide to Paul's interesting work. We know that it degrades over time, or we know with age as people get older, and in particular in pathologies of aging, so Alzheimer's disease and mild cognitive impairment. Normal aging as well, we find deficits in spatial navigation. The root substrate of this appears to be the hippocampus, so that brain region that we think of as being involved in memory. In particular, it's involved in spatial memory, our perception of space. This comes from seminal discoveries of place cells in the hippocampus showing that there are cells that are tuned to specific locations in our environment. So we know that these things degrade, and one consequence of this may be a change in navigational strategy as we get older. So there are two general broad strategies for navigating in your environment. There's what's called the allocentric view and the egocentric one. The allocentric view is using some type of topographic map, a representation of space, so that you can know where you are relative to where something else is. The other is egocentric, so that's centered on the person. This is a route-based learning, like a series of directions, like I have to make 2 rights, a left, and then go straight to get to my location. The benefit of the allocentric strategy is that it's flexible. If I'm somewhere else, I can still navigate to my location, whereas the egocentric one, although it's easier to memorize, is inflexible. If one of those locations or steps is blocked, you don't know how to overcome it. As we get older, we tend to rely on the egocentric strategy, which is because the allocentric one is beginning to become more expensive, more difficult to manage, and we think is related to that loss of connectivity with the hippocampus, potentially. So what I'll note is there is, in aging research, more broadly, this specious notion that people become slower. They are slower in their processing of information. It turns out that's not particularly true. New research is now showing that older adults are just as good at integrating information. They just may be more cautious in committing to a decision, which translates to a longer amount of time in making that decision. And so people think, well, they're slower when actually they're not. They're just integrating more information. So the idea of Paul's work is, can we take people and train them in these virtual environments so that they can overcome the allocentric deficits that they might have to employ a new strategy or come up with some compensatory mechanism. And what I'll note is this relies on something that's a bit of the holy grail in training research, which is what's called far transfer, which is this notion that I can train you on task A and you'll get better on task B. And it turns out a lot of that doesn't work, but there is evidence that in older adults it does work. There is a number of work, and so some of this coming from Adam Ghazali's work out at UCSF and other groups, showing that you can train older adults on VR and video game type applications, and they will show some evidence of far transfer. So Paul's work does have merit in that it can be used to potentially make kind of better environments. But there's one thing in particular that I want to emphasize, which is based on some discussions we were having before, which is going from a desktop where you're just kind of navigating in front of your computer screen to a more real-world environment where you're walking around. And this touches on a comment that Carol made earlier, which is that movement is key. The purpose of a brain is to move. It is to make you move and interact with the environment for the benefit of your survival. And if you're not moving, you are effectively not living. So anything that gets a person moving, whether you are younger or older, is to your benefit. And in these VR environments, if we can build them in a way that a person is actively exploring and navigating in the environment, it may allow them to overcome some of the limitations that are associated with pathologies of aging. So moving is important. VR, however, may not be enough. It might be fine to train someone in an environment. So what I'll note is in your proof of principle work, you did show that still in the novel environment, they showed possibly some impairment. But you would hope that they wouldn't, though, in a virtual environment. You'd hope that they would have been able to overcome that. And so why could that be? Well, it may be that the virtual environment still is not the same as actually navigating in a real, true type of environment. So how do you overcome that? So one of the things that we discussed was going from VR to AR, so augmented reality. These are kind of things like Microsoft HoloLens or other pass-through technologies where you can overlay some type of heads-up display to your retina or to whatever you're observing to help you to navigate. Those technologies are far off, but they are coming. So it could be that with technology like this, you could eventually reach a point where people are able to better navigate, better find things, and better overcome some of these limitations. But again, the key is actual movement, actual navigation in the environment. Without that, there won't necessarily be these connections that we're talking about, or building better connections to overcome deficits in allocentric navigation. So that's it. I think it's very interesting. I think it's very cool, and I'm glad to have been here. So thank you.
Thank you, Martin. Paul, would you like to respond to the wonderful comments?
Shall I come sit down?
Yes, please.
Okay. Yeah, I mean, no, I think it's a great characterization and kind of a continuation of what we were talking about. But yeah, I mean, you know, I do think immersive virtual reality, I see it as a very powerful tool. We can answer a lot of questions. It's really good in a laboratory setting because we can kind of get that precise experimental control. But I don't want to, you know, say that it's the end all be all. I think certainly certain research questions, there's a lot of validity to doing this. You know, I'm really excited about this idea of augmented reality that kind of blends virtual reality with real world, and can kind of still gives us some ability to manipulate the environment. But then, you know, some of these questions might be better addressed in real space, especially when we're trying to maybe, you know, if we're thinking more translational applications. So can we identify some of these spatial markers that might identify those that are at the heightened risk for Alzheimer's disease? You know, so I guess, yeah, I don't want to come across that VR is the only method, but it's a very powerful tool.
Thank you, Paul. Yes.
Am I on?
Yes, you are.
Great work, Paul. Thank you very much. I really appreciated you putting the individual dots for the people on there, because I think it makes an incredibly important point, and I know you're aware of it. Spatial navigation is not impaired in aging. Spatial navigation is impaired in some individuals. And in every one of your slides, I think, pretty much, there were some older adults who did just as well or even better than the best young individuals. And what you get is this trailing off into the distance of those. So what are your thoughts on that? What's it related to? What are you going to do with it? What are you thinking about that?
Yeah, no, you're absolutely right. There's huge individual differences, right? And you know, you'll have a lot of older individuals who perform as well or better than your average younger adult. So, you know, I think one thing we've yeah, I mean, I know there's been some work kind of looking at, you know, traditionally super agers have been defined based on memory performance, right? I know there's some interest in trying to identify, you know, super navigators. So those people that just, for whatever reason, what are the factors that help us maintain this ability? But yeah, I think it really just kind of underscores that there's a lot here, and I think it's kind of difficult to tie it into a simple behavioral or neurodichotomy, allocentric versus egocentric. There's a lot of factors that are at play. You know, so yeah, I mean that's really where we just need to collect more data, and you know, maybe trying to capture some of the psychophysiological and biometric data. You know, currently we're collecting blood samples that will allow us to, you know, look at potential Alzheimer's pathology and see, does that explain any of this this pretty significant inter-individual variability. So yeah, something we're definitely very aware of, but at this point it's a big question mark.
Thank you, Paul. Yes, Ray.
I just want to make sure I understand a piece of your data before I ask my question. You had data that showed, I think it was with the was being able to stand still. You had them tilt their head back, and one was with and without the VR, and the VR always seemed to perform worse.
So we had, it's called the postural sway test, and people are basically standing upright, and we systematically have them start by eyes open, then eyes closed, then put their feet together so you have smaller base, and then tilt your head back. So, and we did that both in real space and VR.
So I wonder if the VR environment couldn't affect that, because sometimes it locks and you don't change your point of view when you tip your head, or if you tip your head back and the weight of the VR glasses is just creating some sort of reflex to try to respond against that.
Yeah, I mean, that's one reason we're doing this, right? If we're trying to argue that we can use virtual reality to mimic some of these more naturalistic settings, this seems like an important question. And I think that point, yes, I agree with that you are wearing a headset, right? And it's not, the weight is not negligible. And that's why I was a little surprised to see that that more extreme condition, the vestibular system, it was actually the impairments were not as severe in VR than they were in real space. I would have predicted the exact opposite. So again, small sample size, so we'll see how that pans out. But I think that's a good point, and that's exactly why we want to look at this further.
Thank you, Paul. Other questions? Yes, Carol.
Picking up on Lee's sharp eye for the data and the variability, even old rats show individual differences. And you have to age them to extreme ages where you're getting everybody, all the old ones are poorer than all the younger adults. So what age range are you looking at in your studies? You never mentioned that, so I was just
Sorry,
curious.
we have been looking at 65 to 75. So yeah, that could be an option if anybody wants to throw us some money to do the old, so like over 80, over 90. Absolutely.
So Paul, what's that in rat years?
Oh, I don't know.
Oh yeah, 30 months. Oh boy. Poor rats.
Yeah, I have a question. Thank you for your work. I actually always think that older rodents just like to swim, and they're not as anxious to get to the platform. We never really know what the rodents are thinking, but that wasn't my point. The connection between early cognitive impairment and functional issues and so on is an important area to look at. I'm not sure I understand the reason for the body-worn sensors and mobility and functional mobility and so on in terms of spatial. Could you make that connection for me, or what you're looking for with those body-worn sensors?
Yeah, I mean, at this point, it's certainly more exploratory. But the idea is that there might be these really subtle changes that, are difficult to pick up without this kind of technology. So the idea is that as we get older and as we're having people on our test kind of navigate, move around, do things like, differences in gait patterns and, fear of falling, stuff like that. How does that contribute to some of these, does that give some kind of correlate of spatial disorientation? It may not, but it's more of a, just kind of a prediction at this point.
And walk.
Yeah, absolutely.
And
so yeah, if
that more closely can identify folks who may have cognitive impairments. Is that sort of the same?
I think that could definitely be one mechanism there. Yeah. So if you are kind of more, worried about fall risk and kind of maintaining that balance, even if you're not conscious of it, if it just takes more, kind of cognitive effort to maintain that, then that might be kind of drawing attentional resources away from the task at hand. So there's probably, then that could be another, there's empirical ways to look at that. Absolutely.
Thank you, Paul. Mindy, other? Yes.
Thank you. Hi, my question is whether you looked at any visual spatial measures that are related to your data, and I feel like it would be really useful to look at some kind of brain measures, like perhaps gray matter volume or white matter connectivity, to get at those individual, variables that may impact the individual performance.
Yes, so all of our participants undergo neuropsychological testing in several different domains, one of those being visual spatial abilities. Haven't really looked at that in relation to this data yet, but we do have that. It's separate studies, but we do have a lot of overlap in our participant pools. We do have some studies where we're looking at brain structure and function, including high resolution images of the hippocampus and entorhinal cortex, regions that we know are important for navigation. So certainly with such small sample sizes, there probably wouldn't be much there, but that is something we are in a position to be able to look at down the road.
Thank you. Yes, question at the back.
I'm just curious, the retention, this can be very interesting to see longitudinally, to see those data, individual differences and the changes over time. And the retention of the participants can be very important. And what's your take on, with the participants now?
Well, first of all, I absolutely agree. Everything that we've done is cross-sectional. Longitudinal really, I don't want to say it's gold standard, but it's a very important next step. So looking at longitudinal change within individuals over time, because that can give us a much more powerful estimate of what's really going on in the brain aging process. And as far as retention, the studies that we've been doing right now are kind of one-off studies. They just come in for one session. But I will say people love it. Our older, there's a lot of, I know this kind of came up earlier, maybe we always ask, and we get measures about prior experience with both computer gaming and also VR, just to kind of have a measure of, we can look at later. And a lot of our older adults are a little apprehensive. And certainly there's a selection bias. We get kind of the more, the people who volunteer to come in, but maybe a little bit of apprehension. Once they do it, a lot of them really, really love it. Yeah. So anyway, that doesn't really speak to retention, but I'm hoping that we would be able to continue to bring them in.
Are there any other? Yes.
I don't want to hog the mic if other people have something to say, but it does. Another point that you made at the very beginning about ecological validity and how important that is. You're finding that when you allow older adults to actually move, that they do much better, and it's actually reminding me of some studies that I think are Kathy Insel about prospective memory, where in the lab, most older adults really don't do well on prospective memory tasks. But when you take it into the real world, as Kathy did, right? I should let you tell this story about asking older adults to monitor when they're taking their medications. They don't have any problem. So it's really a critically important point of finding ways to make these things more real. Yeah.
Yeah, I agree.
Yeah. Do we have any online? Okay. Well, I just have two closing comments. First, I want to start with Homer Simpson and the Quickie Mart. And the fact is, Homer never ages, so I would really like to see him tested. I think that would be an interesting one. And the other one, going from the ridiculous to the sublime, one thing a theme that I've heard here is, and I think, Martin, you said it, was that the older people perhaps were more cautious. And I would say that maybe there's wisdom in that. And I just wanted to say that I think we live in this world, where we don't consider the wisdom of our elders. And I think that that's a whole area that we could be exploring instead of the deterioration, the actually enhancement as we get older, just on that more positive note for us also. Thank you very much.